All right, so we are going to get started today with data visualization in R. And there's a couple of packages that you're going to need to install before we can do this tutorial. So I want you to install the GG Themes package. So that's GG Themes, and we'll go ahead and run that. And the goal of today is not necessarily to cover every single data visualization that is out there, but rather we want to cover enough of different visualization types to make sure that you have a good grasp on how you do visualization in R. So we're going to work with 3 data sets. The first one is this really famous data set called the iris data set. And this is about flowers. The second is going to be about chicken weights, just because we needed a categorical variable to visualize. And the last one is going to be a time series. So if you're working with numeric data, you probably want to really pay attention to the iris data set because you're going to come back to it when you're working on your project. If you're working with categorical variables, then you're probably going to want to come back to the chicken weights section. And if you're working with time series, you're probably going to want to come back to the very end when we're looking at air quality and World Wide Web usage. That's not to say don't do all of them, but just that's where you probably want to pay the most attention. Now, that said, we're not going to cover everything that you want to do with those different data types, but we're just going to kind of give an overview and an introduction. Okay, so now your GG themes should have installed. So we'll go ahead and comment that line out in case at any point we want to run our entire code again. And we are going to call a whole bunch of themes. The first, or a whole bunch of libraries. The first, as you probably suspect, is the GG Themes library. And we'll use this a little later on. This gives some pre-made libraries that you'll use. The second is the Tidyverse library, as usual. We also want the Dippler library and the Lubridate. So we've used all these other libraries before. The DPLYR and the Lubridate library. Library and Lubridate. All right. So we've used all these before. They should be pretty familiar by this point. So we'll go ahead and run those, load those into our environment. Okay. So we will be using the iris dataset. And let's find out a little bit more information about this. It's actually a really famous data set at this point, probably because of its popularity in R, but it's the petal length, the sepal length, length and width for 50 different flowers for all 3 species of irises. So kind of cool. We will make sure to use the species and the petal length and width and all of that. Okay. So we're going to first load the iris dataset into our environment. We'll call data and then iris, and go ahead and run that. And we want to inspect our dataset, so we are going to glimpse it, glimpse iris, and we will check out the head of iris, just to understand how it's structured. Run both of those, and as we see, we have 150 observations of 5 variables. Our variables are sepal length and width, petal length and width, and the species. You see these come in as decimals, and these come in as factors. And the head of it is organized as we would expect. We have some numbers, and we have the species over here as a character value. Okay. So now that we have that loaded in, we are going to make our first plot. So go ahead and type ggplot. And we've worked with the ggplot library a little bit before, but just to remind you that whenever you use ggplot, you write ggplot, and then the first thing that you pass it is the data set. So for us, our data set is just called iris. If you loaded your own data set into R, then it would be whatever you called your data set. And then we pass an aesthetic, and every single plot needs an aesthetic. And our aesthetic is our X, our Y, all of our variables that we're putting onto our plot. And this could be X and Y. This could also be like color for a categorical variable or size for an ordinal variable. So for us, we want to look at the sepal length versus the sepal width. So we'll go sepal.length, and then y will equal sepal.width. And if you wanted to, you could have put the iris and $sign in front of each of those variables, but we're just going to leave it like that. And then we're going to add a geometry. And our geometry says what kind of shape we want to use. So do we want to use a point? Do we want to use a line? And we're going to use a geom point and just leave it blank like that. So we'll run that, and then we get a bunch of points. And okay, so we know that there's 150 data points in this set, but that doesn't look like 150 points. What's going on? Well, as it turns out, a lot of our flowers have the exact same sepal length and sepal width. So, in order to see all of those, we have a classic case of overplotting here. One thing that we can do is jitter our data. And jittering our data means shaking it a little bit, moving it slightly one way or another. So I'm going to do the exact same thing, but I'm going to change my geometry. So I'm going to go ggplot, I'm going to pass the iris data set, I'll give it the aesthetic where x is equal to sepal length and y is equal to sepal width. We're going to start copying and pasting those, and then I'm going to add the geom jitter because I want it to be shook up a little bit. Now what that's going to do is it's going to move the points slightly over to the left, to the right. A little bit later we'll get more scientific about that, but for now we're just moving them randomly. But it would be really helpful to me if I could still see like kind of where they all are. So I'm going to make them all a little bit see-through. And I'm going to say alpha equals 0.6. And alpha is the transparency. So it's the transparency of your points. Go ahead and run that. And what we see here is the same plot, but rather than having all of those points on top of each other, we can see that these ones are overlapping a little bit. There's probably a couple here that are really, really close to each other. We see a cluster right here that we wouldn't have been able to see otherwise. So by jittering and setting the alpha, we're able to see more of our data than we would have otherwise. This is a really great strategy for any time that you have an overplotting situation, that all of your points are really clustered together. All right, so now we have two variables, but wouldn't it be nice if we could have a third? If we could, say, tell which of these points were of the first type of iris, the second, or the third. So we can go ahead and do that. But we're in a Cartesian plane. We only have x and y, so we're going to have to use something else. For this case, we can use color. Color is a really great way to show your categorical variables. So we'll go ggplot, we'll pass it our data set iris, we'll give it the aesthetic where x is equal to sepal length and y is equal to sepal width. And now our color is going to be equal to species. Now I don't remember if species is capitalized or not, so I'm going to go down here, and it looks like it is. So color is equal to species. Okay. And then I'll go ahead and add my jitter geometry. So I'll go my geom jitter, and I'll still put alpha equal to 0.6 because I still want to be able to see where where the points are right on top of each other. All right, so Now that we've broken these out by color, we can see that this cluster actually is a completely different variety of iris. So it's not that, all irises were randomly distributed through here, but by plotting this categorical variable, we can start to see some shapes taking their form. So we see a blue cluster here, a green cluster here. To the human eye, these flowers are probably not terribly distinguishable by their sepal length. This cluster might be a bigger flower, but these two, it's probably going to be really hard to tell the difference between this one and this one without other factors. But once you're plotting these ratios, you can start to see the patterns emerge. Pretty cool. All right, but colors are hard to see. So it would be a little bit better if, rather than using color, we could break these apart into different plots, right? Because I can't really see too well if I want to just look at the green or just look at the blue. I can't really see that too well on this plot. So I'm going to make 3 separate small multiples. This might be my favorite thing about ggplots, is the ability to make small multiples so easily. So we're going to call ggplot, we're going to pass our data set, the iris data set, and then we're going to pass the same aesthetic. X is going to be equal to sepal length. You're probably getting really tired of typing the exact same thing, and we are going to deal with that in just a minute. Y is equal to sepal width, and color is equal to species. All right, I'll close those and then add the geom jitter, and my alpha is still going to be 0.6, and then I'm going to add to that the facet grid, and then I'm going to say dot tilde species. And this essentially says by species. That dot tilde syntax indicates by. So I want to break these apart by species. If I were to break these apart by sepal length or sepal width, I'd get like so many different plots. I wouldn't want to do that. Generally, when you're making facet grids, you want to break your facets by a categorical variable. Okay, so we'll go ahead and run that, see what happens. And we end up with 3 plots, one with the setosa, one for the versicolor, and one for the virginica, right? So all 3 of our species are broken out into different plots. This is a really excellent way to deal with overplotting generally. All right, it's great to have these plots, but what if I wanted some kind of a line to explain the trends that I'm seeing? I probably want what is often called a line of best fit, a linear regression. I want to be able to predict what other flowers might look like. If I got another flower that was somewhere along here, I want to say, oh yeah, if I know its sepal length, I should be able to predict the sepal width of a virginica flower, right? So let's go ahead and find that line. And R makes this super simple. So we're going to build the exact same plot, and rather than typing it again, I'm going to copy all of this, and I'm going to paste it. I'm going to add to this a stat smooth line. And I'm going to say the method is the linear method. Method equals LM. Your LM should be in quotes, and it really just means that I want a linear line. Later in this tutorial, we will deal with lines that are not linear. All right. The next thing I'm going to pass is SE equals false. And SE here stands for standard error. And what standard error would do would be, it would give you buffers around that line of basically what's the standard deviation with respect to a line rather than a point. So it gives you a buffer all the way around that line. And I'm going to make the color equal to, let's say, black. All right. We'll go ahead and run that. And we get our 3 lines describing the relationship between sepal width and sepal length for each of these 3 species. Pretty cool. But this method was really slow. It'd be great if we could add different features and play with our variables, change up our geometries in a little bit more rapid of a way, or a little bit more portable of a way. So the first thing that we can do is assign a variable to our base things that we always have in our plot. So I'm going to call my variable irisPlot, and I'm going to assign irisPlot to ggplot, and then the dataset iris, and the aesthetics, x equals sepal length, y equals sepal width, and color equals species. Okay? Because I'm going to use this over and over again, and it's going to be a lot easier if I can just carry it around all together. So let's try that out. Let's try out irisPlot plus geom point. See what we get. That's because I made a big typo here. irisPlot plus geom point. And we have to remember to run all of it. And then we get our points. And if we do irisPlot plus geom jitter, then we get the same plot that we had before, with our points slightly jittered. I'll change my alpha here. My alpha equals 0.6, and they're shook up a little bit, and you can see through them. So what R is doing is adding a random amount of variation in order to move the points around a little bit so that you can see them more easily. So we want to standardize that random amount of variation. So we are going to define a position function. I'm going to call it POSN, and I'm going to assign it to the jitter position. So position underscore jitter. And I'm going to specify the width to be 0.1. You can do this in a wide variety of ways if you need your plot to be particularly precise. However, generally it's just good practice to say, hey, I have moved these uniformly a certain amount one way or the other. So I will go ahead and run that, and it'll just store that variable for us. And now we will call it. So we'll call our irisPlot. We will add the geom point, and then our position for our geom point will be the position variable that we set earlier. So you'll notice here that we no longer need the geom jitter. We've moved to the geom point with a specified position. And the difference is geom jitter adds a random amount of variation, whereas geom point is the same point variable, and we've passed a specified amount of variation. So we'll go ahead and run that. And what we see is basically the exact same plot. Nothing has really changed much here, but what you can see is that we've standardized our points. Notably, you can't see through them, so you probably want to add back the alpha equals 0.6. And we'll go ahead and run that again. And we get the plot that we were expecting. Excellent. So we are going to get a little bit fancier, and we're going to do some statistics on our plot. We want to find the midpoint of the sepal length and the sepal width. And the midpoint that we're going to choose is going to be the mean. So I'm going to set a new quantitative variable, and it's going to be iris summary. And I'm going to set my iris summary to the aggregate of the iris data set, but I only want columns 1 through 4. I don't want all of the columns, because if we remember back to our iris data set, the first 4 columns of data were quantitative, but the 5th column was qualitative. And I don't want to perform any statistics on my qualitative data, only on my quantitative. And then I'm going to tell it what to do with that. And I'm going to say, make a list of the iris species, the iris species data, and calculate the mean. So I want the mean of columns 1 through 4. And it looks like I somehow got an extra set of parentheses in here that I don't necessarily want. And I'm going to assign the names for this iris summary. And I'm going to say that put them in the first column. So I want to make the most left-hand column, the names, and those will be the species names. So let's run this and see what this actually looks like. It's pretty small, so we can just call the entire data frame. Okay. So we'll run this whole block of code, and what we see is we got the average of the sepal length for the Setosa species, and then we have our names of Setosa, versicolor, and virginica. So we've calculated the average for each of our 4 columns using the iris 1 through 4. We grouped them along the species, and we found the mean, and then we set the name of each row equal to the species as a column. So we line those back up. All right, so now we have the mean value for each one of these. So let's go ahead and plot that. So we're going to take the iris plot that we've been using all along, and we are going to add the geom point to it. We're going to specify the position equal to the position function, our alpha equal to 0.6, and so far all of this is exactly what we've been doing. So now let's add our new feature. So I'm going to go plus sign, go down to the new line, and I'm going to add another geometry to the same plot. So I'm adding another point geometry, but this is going to have a different data set. And the way that you do this is you specify that the data for this geometry is the iris summary, right? And then I'm going to specify the size. I'm going to say shape is equal to 21, size is equal to 5, and the fill I'm going to say is equal to gray. All right, so what I've done here is I have my original plot, and I added my first geometry to this aesthetic, this data, this aesthetic, and this plot. And then I'm adding a second geometry on top of the first geometry. And the second geometry is where the calculated data comes in. And I don't necessarily want to have 2 plots, rather I just want to have a second geometry on my first plot. So we'll go ahead and run that. And we see that we have these circles in the middle. And each of these circles are the mean that we had calculated before in our iris summary. There's a few other things along these lines that we can do. You can do things like draw a vertical line in order to say what's to the left or to the right of the mean. So you can do things like iris plot and add a geom point layer. It's the same geom point layer with the position equal to the POSN and alpha equal to 0.6. And then add to that the vertical line from the data is the iris summary. And the aesthetic, here you actually pass an aesthetic because what we're looking for is the x-intercept. So the x-intercept equals sepal dot length. So this will draw a vertical line for each sepal length. Go ahead and run that. You'll see what I mean. You can change this line type by specifying line type here after the data before the aesthetics. You can say line type equals, let's say we want like a dashed line, make it 3. And you can do the same thing for a horizontal line. I'm not going to illustrate that. It's pretty easy to find. Okay, so up to this point, our plot has really been exploratory. A plot that looks like this is most often really just for you as the researcher to get some information out of your data. Because oftentimes it's much easier to understand your data set by visualizing it rather than just looking at a table of numbers or even some individual numbers. A lot of times the visualization will give you a lot more information, help you understand the distributions and the relationships. But that said, often you will want to make your table for publication. So let's go over some strategies to do that. So what we want to do is clean up the formatting and remove some of the non-data ink. If we follow Tufte's principles, you know, we shouldn't have this gray background, and the sepal.length is inappropriate. And what we actually want to do is standardize all of our labels, make sure that there's no ink being used on this page that isn't for communicating about the data. So one thing that you can do is add coordinates. So here we're just going to do our iris plot, and we're going to add to that the point that we've been using, so the geometry point, and our position will equal the position, alpha equals 0.6, and we will add to that a scale y continuous and a scale x continuous. And our scale y continuous, first we're going to pass a label, and it's going to be sepal width, and we'll give our measurement. Our measurement was in centimeters. And we'll specify our limits, and our limits will be from C 1, 5. What this C does is it makes it a special kind of list. It makes it an array. Not really important for right now, but just know that you need the C in order to give it a range like that. We're going to expand our limits from 0 to 0. Okay. And we're going to do the same with the x. So we'll go with scale x continuous, and we will say that is sepal length. Specify our unit of measurement is in centimeters. Our limits here are more appropriately from 4 to 8. So we'll go C from 4 to 8. And then our breaks here, we want to have a sequence that starts at 2, ends at 8, and there's a major break every 2 units. So we will go ahead and add a comma there, and we will expand again. Breaks equals, not parentheses, equals, and we're going to expand again from 0 to 0. Okay. And then we'll make sure that our parentheses all worked out. It looks like I have an extra set of parentheses here. That is a chronic problem. All right, and then we're going to add coordinates, coordinates equal. Okay. So this means that the number of units on the x-axis is equal to the number of units on the y-axis, which makes our Cartesian plane overall much easier to read. So we'll go ahead and run that. And you might have noticed that I had a typo. Expand does not have an L in it. It's just expand like that. So if you run that, we get this much tighter and much easier to read plot. But you'll notice that it would be much easier to read if we broke these apart. So we should probably add faceting to our plot up here. So I'm just going to go ahead and add that to my plot here, the one that's already written, and I'm going to say facet grid, and I'm going to say by species. And this is going to make our plot much easier to read overall. And you probably know that if we do that, we don't necessarily need to jitter our points in the same way. I'm going to leave it for the time being, but just know that if you don't have the overplotting problem, then you probably don't need to deal with overplotting. All right, so those labels honestly are not so great. So let's fix our labels, okay? So I'm going, rather than typing this again, I'm just going to add on to the code that we already wrote. So after the coordinates equal, I'm going to add the value labs, and I'm going to pass x equals sepal length, y equals sepal width, and color equals species. Okay. And I've just added this directly on to the code that I already wrote here, because as you will see, with ggplots, all you're doing is continuing to build on the thing that you've already started. So we'll go ahead and run that, and we get much clearer labels here on each of our plots. We get a capitalized species. Didn't matter so much here, but this is how you specify your labels. All right, so we're going to add a theme. You can specify your theme line by line by line. I'm going to suggest not doing that because it's really annoying and time consuming. If you are interested in building out your own themes, go ahead and look in the notes for this lab where I've built out an entire theme from scratch. However, we are going to use some built-in themes. So here, just for illustration, we're going to go iris plot plus geom point, our position equals the same position, alpha equals 0.6. And then we're going to use one of the built-in ggplot themes. I'm going to use the theme Tufte. As you saw, there were a lot of theme options there. I encourage you to play around with them and see what you like the best. But we're going to use the Tufte theme because it's there. And you'll notice with the Tufte theme, we've lost all that background information. We've lost all of the lines because he is a big proponent of making sure that there's no excess, aka chart junk. Some of that stuff is important visual scaffolding, so don't take Tufte wholesale, but it is good to think about. You can, of course, take this entire plot that we built before and use the Tufte theme. But you'll note that the coordinates are actually going to conflict with each other because themes have coordinates built into them. So let's see what happens when we add the Tufte theme to our plot that we've already specified the coordinates. Okay. And that one had been broken out in facets, but we see that the coordinates that we specified overrode the Tufte coordinates. And this is an important thing to be aware of when you are using themes, is you can override them by explicitly specifying any element within your plot. All right, so I encourage you to play around with themes a little bit. I encourage you to look at different variables in relationship to each other. For this lab, what I would like you to do is to plot the petal length and petal width against each other. So make a plot similar to this. You can go ahead and choose to use facets or choose not to use facets, whatever you think is more appropriate for the data, and use one of the themes that are in the built-in themes in R. So use ggplot with the same data set and practice using ggplot and look at the petal length and petal width variables against each other. This should be a pretty simple adaptation of what we've already done. Be sure to save that plot, and that's going to be part of what you turn in for the tutorial this week. All right, so we have completed our work with the iris dataset. We are going to move on to much shorter components of this with the chick weight and a couple of time series. All right, so we are going to move on to the chicken weights dataset. What this looks like is we are going to look at what the chicken weights is about. It's actually about feeding of chickens. So go ahead and run that. And it's weight versus age of chickens on different diets. They have like 4 different diets. And this is read in as a factor variable. And this is what we're interested in. What role does diet play in chicken weight, where diet is a categorical variable? All right, so we are going to call the data chicken weight data set. Go ahead and run that. Chick weight, not chicken weight. Call it like that. There we go. All right, so, and I'm going to just start out by specifying both my data and my aesthetics for my plot. And I'm going to call this chicks. I'm going to ascribe chicks to ggplot, and I'm going to pass the chicken weight data set, and I'm going to say my aesthetic is equal to my x will be equal to the chicken weight and the weight variable there. And I'm just going to make a histogram. I just want to see like what is the distribution of my chicken weight. So I'm going to go chicks, and then I'm going to add to that the geometry of a histogram. All right. And I'll go ahead and run both of those lines. And I get this warning down here that says stat bin using bins equals 30. And it tells you to pick a better value with bin width. So we're going to do that in just a second once we look at what's going on with our plot. So it looks like the chicken weights are most of our chicken weights are quite small. They're down here in what looks probably like 50 grams or something like that. And then it tapers off as they get larger with this one outlier here. This is probably a function of age. There's probably younger chickens, more younger chickens than older chickens. But we'll see as we dive into the data a little bit more. Right. So let's go ahead and take our advice and calculate our best bin width. So what I'm going to do is I'm going to use this function diff, and I'm going to pass it the range of the chicken weights, and I'm going to divide it by 30. Right. And I have an extra set of parentheses in here, chronic typo, divide that by 30. And what that's doing is it's taking the difference of all of the weights across the entire range and giving us this number. So when we ran that, it didn't save it anywhere. The entire point of this is to give us a number that we then pass to R. And our number is 11.27. I'm just going to call this 11, and I'm going to specify my bin width as 11. So I'm going to take this same plot, this chicks plus geom histogram, and I'm going to specify my bin width as 11. Go ahead and run that. We get a very similar distribution here. We no longer get the error, which is good. But you'll notice that where our plot before had quite a few chicks who were in this like very small category, it looks like it's smoothed out quite a bit. And we've used better binning for our chicks. This is kind of beyond the scope of this course, but in general, the best approach is to use this function of finding the difference of all of the weights across the range and then dividing it by 30, unless you have some very strange data set. But I don't think that you will for quite a while. All right, so we are going to do a little bit different of a plot here, and we're going to make a density plot rather than a simple count plot. So we're going to still specify our checks, and then we're going to go geom histogram, and we're going to pass our histogram an aesthetic, and our aesthetic is going to be y equals ... density ... and what this is doing is actually calculating the density of our chick weights rather than the plain count. Take a look at this and see what it does. It looks very, very similar, but again, this curve has smoothed out just a little bit to look more like a logarithmic curve. So as you can do it, you can visualize your histogram either by count or by the density across the entire population. It's just a slightly different way to make your visualization. All right, so now that we have an understanding of how our weights are distributed, let's understand the relationship between weight and diet type. So I'm going to make another histogram, but I'm going to add to my histogram a fill based on the diet type. So I'm going to call my ggplot, and I'm going to pass my chick weight dataset. My aesthetic is still going to be x is equal to the chick weight, so the weight of all of our chicks. But now my fill, no, it's not an x, it's a fill, and the fill is going to be the factor chick weight and then diet. And I'll close up those, and we'll add to that our histogram, our geom histogram, and our bin width will again be equal to 11. All right, so we'll go ahead and run that. And we get our histogram with each diet broken down by color. When you look at this, it's actually really hard to parse this. This is a very pretty but relatively uninformative graph, even though you'll see a lot of these out in the wild. What's going on here is that the diet number 1 is layered on top of diet number 2, on top of diet number 3, on top of diet number 4. So unless there's some really radical differences, this will never tell you very much information of the relationship of diet 1 to diet 2, and if one results in a higher chick weight than the other. Because really, once they're stacked on top of each other, your eyes and your brain cannot reconcile which one is longer. So even though this is quite pretty, it's not actually that informative of a graph. It might be better overall even to do percentages. So let's fill all the way to the top. This is actually quite a bit more complicated because, as you see, we're going to have to do some mathematical transformations within our second geometry, or within our geometry. So let's start by calling our ggplot, and we're going to pass the chick weight data set, and our aesthetic is still going to be x equals chick weight weight. And our fill is still going to be this factor of chick weight diet. Right. We'll close all three of those, and we'll add to this our geom histogram. But within our histogram is where we're going to need to do some transformations. So we're going to specify those transformations within the aesthetic. Our y is going to be equal to the count divided by the sum of, oh, you don't need the periods around the sum, sorry. The sum of the count. The reason you don't need the periods around the sum is because it's actually not doing a transformation on the variable, it's doing a transformation on this calculated number here. And we'll close two of those parentheses. So we'll close up our count and we'll close up our aesthetic. And then we want to specify, just as we did before, that our bin width is equal to 11. And now we're going to specify a position. And our position is going to be fill. Because what we want to do is fill this number, the count, divided by the sum of the count, which, as you probably have already guessed, works out to be the percentage or the proportion. And we want to fill that on top of each other. We want to fill it all the way to the top. So we'll run that, and what we find is that we have a percentage graph. Again, this doesn't actually tell us that much because our eyes are very awful at reconciling the difference between this distance and this distance. But what this does tell us is that, first off, there's this big blue band right here, so something going on with this weight and diet number 3. And we see more of the blue generally as we get down here. We get over here into the bigger weights. So maybe we can assume that diet number 3 results in a fatter chick. Alright, so that's all that we're really going to do for the categorical variables with this. Now we can look at chick weight as a function of time. And I'm going to set my chick weight time, and I'm going to assign that variable to ggplot, and then I'm going to pass the chick weight data set. My aesthetic is going to be x equals chick weight weight, and y is going to be chick weight time. And then I will run this, and that sets up my base plot, and I can add to that a bunch of geometries. So I'm going to add to my chick WT the geom jitter geometry, and I'm going to specify my alpha as 0.6. And if I run that, what we find is all of the different chick weights against their age. So the time is actually the age, how many days the chick has been alive and how much weight it got to. As you see, there's a couple little outliers. Maybe these were some underweight chicks, chicks that didn't grow. But as they got older, their weights became more distributed. We can already see from this model that it's probably not linear. There's probably a logarithmic function going on here. All right, so what I'd really like to understand is what that logarithmic function is. So I'm going to go up here, up to my chick weight function, and I'm going to add into my base plot, I'm going to add color is the diet. Okay? Because what I really want to understand is the relationship between age, weight, and diet. So I'm going to say color is chick weight diet. I'll run that again, and then I'll run my chick WT with the geometry, and we see that diet 1, 2, and 3 all have different colors. And we don't see any obvious patterns here between diets 1, 2, and 3, other than most of the skinny chicks are on diet number 1. So maybe we can assume that diet number 1 creates a smaller chick. Obviously, we'd need to do more analysis before we get there. All right, so the next thing I would like to know is I would like to know what the relationship is here. So I'm going to take this same plot, this one that has the chick weight, the geometry, and I'm going to add to that stat smooth. And this is going to give me a line that is the line of best fit for this entire data set. I'm going to ask it for a linear line, and I'm going to specify the color as gray. And just so you can see what it looks like this time, let's set the standard error equal to true. We'll change that soon, but sometimes it's nice. So we see that we have this very linear line for this very not linear data. So we know that this probably doesn't actually fit our data set very well. We're looking for something that's a little bit more curved. And R actually comes with an auto fit function here. So rather than specifying a linear model, let's try an auto. Let's see what we get there. And I'm going to set SE back to false because the standard error sometimes makes it really difficult to read. Okay, so let's see what I can do with auto. This actually looks a little bit better because what we see is that the chick weight increases very quickly in proportion to its age, and then it kind of tapers off. And that does actually fit our data quite a bit better. You can investigate all the different ways to create this line by looking at the stat smooth documentation. Run that and you'll get the documentation here. This actually came up on the Help tab, so we're going to go back to the Plots tab. But if you ever want to reference it later, it's over here on the Help tab. All right, so now it's not actually that helpful for us to have these all on the same plot. It might be easier to compare them if we break these up into different plots. So we are going to go ahead and jitter this, or facet this data. So I'm going to go back to this plot that I created, and I'm going to add to it facet grid. And then I'm going to facet it by the chick weight diet, because that's our categorical variable and therefore the best candidate for faceting. And it looks like I have a typo here. It's facet grid, not fact grid. All right, and we see here that all 4 of our plots have been broken apart, And it is a little bit easier to tell them apart, but not necessarily that much easier. But what this did was it gave us a different line of best fit for each plot, which is really noteworthy because you could have a linear relationship with one and a non-linear relationship with another. And faceting your plots would show you that. All right, so we aren't going to spend too much more time on this, but go ahead and play around with the chick weight data set if you are really interested in the relationship between chicks' weights and their diets. All right, we are going to move on to our last data visualization type, which is time series. So there's actually two different time series that we're going to use. We're not going to get terribly in depth into either one of them, but it'll just give you some experience with how to manipulate time series. All right, so the first one is the World Wide Web usage by minute. When this data was collected is actually really important for our project. So I'm going to type question World Wide Web usage. So what we are going to look at is a time series of the number of users connected to the internet through a server every minute. You will note that this data was published in 2001. It was collected in 1998. So what we know about the internet in 1998 was that it was a very different place. It was much smaller, it was much slower, and you connected through more centralized servers. So that's important when understanding and interpreting this particular data set. All right, so first thing we're going to do, as always, is call in the data World Wide Web usage, run that just to load it in. I want to know the structure of my data set here. And I'll run that. And it looks like I have a time series. I have just a simple time series from 1 to 100 of how many people were connected to this particular server. All right, so what on earth can I do with this? Well, I can't visualize it directly. I have to transform it into a data frame. So I'm going to call my data frame www. And I'm going to assign it to data.frame. And I'm going to say, I'm going to call my first variable usage. And this is just the number of people connected. And I'll do as matrix, because I need to transform those numbers into a matrix and pass the World Wide Web usage frame into it. And then I'm going to say my time, or my use time, which is just time starting at 0. So they took a random 120-minute sample, or 100-minute sample. And my use time is going to be time of www usage. Right? And I will run that. And now let's see what the structure of www is. Okay. And it's a data frame. This is something that ggplot can visualize. Notably, our time series is still just 1, 2, 3, 4, 5, because all it is a sequence starting at 0. 0 is an arbitrarily set time. So we can go ahead and visualize this and see what that ends up looking like. For us, we'll type ggplot, and we'll pass the World Wide Web www dataset, and our aesthetic. X will be the use time, and Y will be the usage. And then let's make a line plot here. So our geom will be aligned because we know that it's continuous as opposed to discrete values. So I'll run that. And what we see is this line chart. This is just the number of users that were connected to the server over a random 100-minute sample. Interestingly, we see this big dip here, and we see this giant spike here. And if we think back to what the internet was like back in the 90s and what servers were like, you know, this is an interesting pattern, and it would be even more informative if we knew what time of day this pattern was collected. Because people were not constantly connected to the internet. Many people did not have internet at work, and the internet was often accessed through cafes where you might buy 15, 30, or 60 minutes worth of internet time. So it would be really interesting to see what exactly this pattern, what time of day this pattern is from. But unfortunately, that is not in our data set. All right, so we're going to look at one more, slightly more complex relationship. We're going to look at air quality in New York City in 1973. This is another R data set, and it's the air quality data set. So I'll run that. And it's not a $, it is a question mark. So question mark air quality. And this is air quality measures from May to September 1973. And it comes in 6 variables. You'll note that there's a month variable and a day variable, but there's no time variable. So we're going to have to make that ourselves. All right, so let's go ahead and load in our air quality data set. Run that. We'll investigate the structure of our air quality data set. And we see those variables, those 6 variables that we were promised. There's 153 observations. And this doesn't read in as a time series, but we know that it's a time series because it's measurements that were taken every single day from May until September. So we can turn it into a time series. Right? So first thing we want to do is let's just check it out. Let's see what happens if we try to visualize it the way that it is. So we're going to pass the air quality data set, and we're going to say that our aesthetic is x equals day, and y equals temperature. Because, you know, if we plotted the temperatures every day, we'd expect from May to September for the temperatures to increase uniformly. So, since we expect that they'll increase uniformly, let's make our geometry a line. Since it's a time series, and they'll increase over time. Okay, so go ahead and run that. And we see something crazy, right? We see up and down and up and down and up and down. What's going on here? Well, this is days. So days starting 1 to 30. If it's going from May until September, we know that there's 4 instances of day 1, 4 instances of day 2, etc., etc. Hence our crazy graph. We're going to have to transform it. Okay, so we need to make a new column. And we're going to call this new column air quality, $ new date. And I'm going to assign that to pasting together with literally the word paste. It means concatenate in other places, but R uses paste, which I just really enjoy. Air quality month with air quality day in 1973, right? Because we can't just have month and day, we also need to have the year. 1973, and then we have to specify a separator for all of these. Now you could have your separator be nothing, but for us, we want to use something. So I'm going to use a dash, because what I'm expecting is that after this, I'll get a character column, a character variable, but I'll need to transform my character variable into a time series. And I know that LubriDate handles dates written with dashes very well. Okay. So I'll run that. Nothing happens. That's fine. And then I have my air quality new date, and I know that I'll have to use the Lubridate package, and I set it up for month, day, year. And it's the month, day, year of my air quality new date. Okay, I run that, and what we see if we glimpse our air quality data set should be our new variable. And it's there. We have our new date, it's a date, and we have this date time for all of the days in our data set. Fantastic. Now, if we visualize this with our ggplot, pass the data set air quality, specify our aesthetic to be x is equal to our new date, and y is equal to our temperature. And since it's a time series, we should use a line, our geom line. And if we run this, what we see is that I have a typo. So I wrote A here rather than X. Sorry about that. Now go ahead and run this line, and we see a much more sensible graph. Here in May, the temperatures are lower. They increase in June and July. There's this one weird day, mid-June, some hot days at the end of August. This is exactly what we would expect from the summertime in 1973. Okay, so the second half of this tutorial, what I'd like you to do is explore another relationship. So either date and another measurement, so date and wind, or date and ozone, or date and solar, or a relationship between two other non-date variables. So either our new date and another metric, or two non-date variables. All right? So go ahead and play around with that a little bit, and you'll have two files to submit today. The first will be on the petal length and petal width from the iris dataset, and the second will be any two variables from the air quality dataset. All right. Let me know if you have any questions, and I hope that you are feeling more comfortable with ggplot and making visualizations within R. All right, and I will see you next week. Bye-bye.